Good morning. In the previous class, we have seen the development of a two-area low frequency control. In the two-area low frequency control, we are having the two parameters we need to control. One is the change in frequency, another one is the change in time and power. If there is any disturbance occurs in the system, these two parameters are going to be varying. So, these two parameters we need to bring back to the normal value by using some proper control. Okay. So, this is the block diagram we have developed for a two-area control. The upper part represents the block diagram representation for the single area. You can say it as area 1. In the down part, the bottom part, this represents the single area low frequency control of the second area. And these two are controlled, these two are connected to the tie line. Okay? The single area 1 and the single area 2, these two are connected to tie line. So we have done the proper mathematical modeling for the changing tie line power, how these two are going to be connected. So here in the area 1, delta F1 of S, in the area 2, the frequency changes delta F2 of S, and this one, that is changing tie line power. So these parameters, in case of a single area, we are going to study only the change in frequency. In case of a two-area system, in addition to the change in frequency, you need to go through the change in tie line power also. Okay, so these two parameters we need to regulate. Okay, so for the purpose, we are going to study the steady state response. Okay, when there is any disturbance occurs in the system, how these two parameters are going to be varied. Okay, so first we are going to study the uncontrolled case. We are going to study the uncontrolled case. So uncontrolled case means delta Pc1 of S is equal to delta Pc2 of S is equal to 0. So the speed changer setting is going to be 0. So there is no change in the speed changer setting. So uncontrolled means free governing operation. From the governor side, you are not going to change this parameter, that is speed changer setting. So you are leaving free. Okay, so that's why this is known as a uncontrolled case. So we are going to study when a step load disturbance occurs on the system. When a step load, so of course the disturbance occurs in the system. For our ease of analysis, we are considering the disturbance is step. The disturbance is of size step. Okay, we are considering it as a step. So when the step load disturbance occurs in the system, both in frequency and the tie line power, we need to study how these two parameters are going to be varying. So in case of single area, we have gone through area control error. Area control error, since it is a single area, the area control error consists of only the single parameter, one parameter, which is the change in frequency. In case of a two area low frequency control, the area control error consists of two parameters. One is the change in frequency, another one is change in tie line power, delta P type. Okay. In the case of a single area, the area control error having only the frequency, change in frequency on the occurrence of disturbance in the system. In case of a two-area system, two-area low frequency control, the addition parameter add will be the change in tie line power, delta P type. If it is from area 1 to 2, you are representing delta P type 1 to. If the change in tie line power is from area 2 to 1, you can represent with the delta P type 2 1. So these are the two parameters which contribute to the area control error in case of a two-area system. Let delta F1 and delta F2. Since you are considering two area, delta F1, one index for the area 1, 2 index for the area. Okay. So delta F1 and delta F2 are the change in frequencies. So these are the change in frequency occurs when the disturbance occurs on the system. Okay. When the disturbance occurs on the system. So in this case, the disturbance means load only. Okay. We are considering the disturbance as the load change. That is of first step. You need to keep in mind. Okay. So because of this load disturbance, the change in frequency will be delta F1 in area 1 and delta F2 in area 2. Okay. So these two parameters. And next delta P type 12. Okay. Delta P type 12, that is a change in tie line power from area 1 to area 2. And delta P type 21, that is a change in tie line power from area 2 to area 1. So just they are in 1 to 2. 1 2 means area 1 to area 2. 2 1 means area 2 to area 1. The power transfer from area 2 to area 1. Of course, these two are equal in magnitude. These two are delta P type 12 is equal to delta P type 21. Delta P type 12 is equal to delta P type 21. These two are equal in magnitude, but just they move in opposite direction. The amount of, for example, if 50 megawatts amount of power is transferred from area 1 to 2, that is delta P tie 1 2 is 50 megawatts, for example. Okay, at the same time, delta P tie 2 1 is minus 50 megawatts. Just the magnitude remains same anyhow, just sign will be opposite. Okay, the direction is in reverse direction. That's why delta P tie 1 2 is 50 megawatts, then delta P tie 2 1 is minus 50 megawatts. Okay, so these two parameters are change in time and powers from area 1 to area 2 and vice versa, area 1 to area 2 and area 2 to area 1. Okay, so these are the parameters we need to study. Clear? Next, so we know the power balance equation. What is the power balance equation? So if there is any occurrence of disturbance in the system, immediately you are going to change the generation from the speed governing side. Okay, so at the initial swing, we will be having some excess energy, that is delta Pg1 minus delta Pd1. This is the excess energy, you can say surplus amount of energy is there. This surplus amount of energy will be contributed into three components in case of a two area. Okay, we have studied this expression also. In a single area, this will be contributed two components only. In the two area, the surplus amount of power that will be contributed into three components. Okay, one is the rate of change of kinetic energy. We have seen the rate of change of kinetic energy. So the kinetic energy means which is stored in the rotating part of a rotor. Okay, definitely this is the first component which will be affected according to the change in load. Okay, the surplus amount of power that will be contributed into three components. One is the rate of change of kinetic energy, that is the first parameter. And the second one is change in motor loads. Change in motor loads which are very much sensitive to the frequency. Okay, there are certain motors which are their speed, their characteristics are very much sensitive to the frequency. If there is any small change occurs in the frequency, then the performance of that motors will get deviated. Okay, so the second part will be the rate of change of motor loads with respect to change in frequency, and the third one will be the change in tie length power delta P tie 1. Okay, so this delta P tie 1 comes in picture in case of a two area only. In case of a single area, this delta P tie 1 will be 0. Okay, there is no concept of second area, there is no concept of amount of power transferred from area 1 to area 2. That's why delta P tie 1 will be 0 in case of a single area case. In case of a two area, this parameter will be exist, delta P tie 1 2. Okay, the power balance expression, this is not the power balance expression. Okay, and the disturbance occurs in a system. So whatever the disturbance means change in load. Okay, so whatever the disturbance or change in load occurs in a system, that we need to met from the speed governing set by increasing or decreasing the generation. So for example, at the initial swing, there will be a surplus amount of power, delta Pg1 minus delta Pd1. Okay, this will be contributed to three components. One is rate of change of kinetic energy. Second one is the change in motor loads with respect to the change in frequency, and third one is the change in tidal power. So similarly, in case of area 2, the same expression can be written like this: delta Pg2 minus delta Pd2. Okay, so this is equal to same the rate of change of kinetic energy in case of a two area system. Single area 2, you can say the area 2. The second expression representation for the area 2. This is the rate of change of kinetic energy for the area 2. The second component V2 into delta F2, that is change in motor loads of area 2 with respect to change in frequency, plus delta P tie 2 1. So which is the change in tidal power from area 2 to area 1. Okay. So under steady state condition, we are considering the steady state analysis. Under steady state condition, so steady state condition means the change of frequency is assumed to be steady state with the value which exists at the t tends to infinity. Okay, the steady state condition means the situation of a system in a time domain that exists at a t tends to infinity. So at this instant, the change in frequency will be settled down to some constant value. Okay, at t tends to infinity, the change in frequency or any parameter, whatever the disturbance in a system, that will be settled down to some constant value. Okay, so that's why in both the cases, this delta F1 and delta F2, these are assumed to be constant at the steady state point. Okay, so therefore on differentiation, delta F1 at the steady state condition and delta F2 at the steady state condition, these two parameters will be 0. Okay. So y means these two are constant at the steady state. At the steady state, at t tends to infinity, these two parameters remains constant. On differentiation, these two will lead to 0. Okay. Next, so here we are taking the assumption that, so this assumption we have seen already, Ksc into Kt equal to 1. Okay, you know, we adjust the linker mechanism. We have some linker mechanism. We adjust the linker mechanism such that Kc into Kt is equal to 1. So Kc1 into Kt1 for area 1. Similarly, Kc2 into Kt2 is equal to 1 for area 2. At the same time, we will assume for the time constant also, Tsc is equal to Tt is equal to 0. Means for area 1, Tsc1, Tt1, Tsc2, Tt2 is equal to 0. So the time constant for the speed governor turbine are assumed to be 0. Why means we have seen in earlier sessions the time constant of speed governor and turbine, these are very much negligible when compared with the time constant of power system. So that's why these two are very much negligible. These will be in the range of 0.2 to 0.4. So Tsc and Tt will be in the range of 0.4. Okay. So while coming to the TPS, which is time constant of the power system, so this will be around 20 seconds. Around 20 seconds. So while comparing these two, Tsc, Tt and TPS, Tsc, Tt are very much negligible. The time constant of the speed governor and turbine are very much negligible when compared with the time constant of the power system. So that's why these two parameters you can consider as 0. So by taking these assumptions, the block diagram will be reduced to, so this will be reduced to 1. Okay. Again, this will be reduced to 1. So likewise you can write. So since we are considering this as 0, delta Pc1 and delta Pc2 as 0, why means we are considering for the uncontrolled case. So that's why delta Pc1 of s is equal to 0, delta Pc2 of s is equal to 0, and then these two blocks are reduced to 1. Okay. At this instant you can write delta Pg1 is equal to delta Pg1 is equal to, so this one multiplied delta F1 of s multiplied with 1 by R. Okay. So this minus will be anyhow here. So therefore delta Pg1 of s is equal to minus delta F1 of s into 1 by R. Similarly for area 2 also, these two blocks will be reduced to 1. Okay. The speed governor and turbine block are reduced to 1. Pc2, delta Pc2 anyhow will be 0 for uncontrolled case. At this instant you can write this delta Pg2. Here you can write this is delta Pt2 and delta Pg2. So delta Pg2 is equal to minus delta F2 into 1 by R. Okay, delta Pg2 will be minus 1 by R2 into delta F2. So that's what we have written here. Delta Pg1 is equal to minus delta F1 by R1. So before, these are expression before applying the Laplace transform. Okay. So delta Pg1 is minus delta F1 by R1, delta Pg2 minus delta F2 by R2. Okay, by reducing the blocks of the block diagram. Okay. So substitute these two in power balance expression. In this expression, we are going to substitute in this expression. So delta F1 will be 0. Delta F dou by dou t of delta F1 will be 0. So this term will become 0. So delta Pg1 you are going to substitute here minus delta F1 by R1. Okay, so minus delta F1 by R1 minus delta Pg1 is equal to, the first term will be 0, d1 delta F1 plus delta P by 1. At the same time, this expression for the area 2 minus delta F2 by R2 minus delta Pd2 is equal to B2 into delta F2 plus delta P by 2. Okay, the first parameter anyhow it becomes 0. Okay, so this is the second parameter and this is the third parameter. So on readjusting, take the common from delta F1. You will take the common of delta F1 D1 plus 1 by R plus delta P by 1 2 is equal to minus delta Pd1. So same case for the area 2, delta F2 V2 plus 1 by R2, and in case of delta P by 21, you can represent this expression as minus A12 into delta P by 12. Okay, so delta P by 21 is equal to minus A12 into delta p times 1 2. So you can represent delta p times 2 1 in terms of the delta p times 1 2. Okay, so that's what we have represented here. Minus A12 delta p times 1 2 is equal to minus delta PD2. Okay, so we are considering this B1 plus 1 by R1 as beta 1, B2 plus 1 by R2 is equal to beta 2. So for our ease of analysis, that's it. Okay, so there is no significance of beta here. Just for our ease of analysis, we are representing it beta 1 and beta 2. Let we are considering both areas are identical. Both areas are identical. So this assumption is taken for the ease of analysis. Okay, analysis for taking the analysis much easier, we are considering both the areas are identical. So therefore, the change in both the areas will be same. Delta F1 is equal to delta F2 is equal to delta F. On substituting in this expression, so we'll substitute here. Okay, here delta F1 you can remove this. Delta F2 also you can remove. Okay, replace this delta P times 2 1 with minus A1 delta P times 1 2. So these two expressions when you represent in matrix notation, beta 1 1, beta 2 minus A1 2, delta F delta P times 1 2 minus delta PD1 minus delta P2. Just these two expressions are represented in matrix notation. So nothing new here. You are representing in matrix form. Okay. So these two parameters we need to calculate. Delta F and delta P times 1 2. So we know some A into X is equal to B. X is equal to A inverse into B. Okay. So this X is delta F into delta F. And the delta p times 1 2 will be the x. So this is A. So multiply means take the inverse of this, multiply on both sides with the B matrix. So this is B minus delta PD1 minus delta PD2. So after evaluating with this expression, you can write delta F as delta PD1 plus A12 into delta PD2 divided by beta 2 plus A12 into beta 1. Okay, just you will get. Okay, Ax is equal to B. We know the matrix notation. If you want to find the x value, x is equal to A inverse into B. Okay, here the x matrix will be delta F and delta P times 1 2. So these are the two parameters we need to find in case of a two area system. Okay, so delta F is equal to delta PD1 plus A1 into delta PD2 divided by beta 2 plus A12 into beta 1. At the same time, you can write the expression for delta P times 1 2 also. Beta 1 delta PD2 minus beta 2 delta PD1 and beta 2 plus A12 into beta 1. So after taking the inverse, you can directly get the expression for both the parameters, change in frequency and change in tie line power. So we have taken the identical areas. So identical areas means B1 is equal to B2 is equal to B. So B means we know rho P d by rho F. Okay, rho P d by rho F. So the change of motor loads with respect to change in frequency. If I considering both the areas are identical, so the change in loads will be same in the both the areas. The change in motor loads with respect to frequency in the both the areas are considered to be same. So that's why you can represent it as a B1 is equal to B2 means both are same for the both the areas. That will be replaced with the B. At the same time, R1 is equal to R2 is equal to R, speed regulation. Okay, so according to load, all the frequencies or speed is going to vary. So that is the speed regulation parameter. We are assuming for two identical areas. So therefore, you can replace R1 is equal to R2 is equal to R. So when you are taking these two are same, as we are representing beta is equal to B plus 1 by R. So beta 1, B1 plus 1 by R1. Beta 2, B2 plus 1 by R2. Okay, when B1 is equal to B2 is equal to B, when R1 is equal to R2 is equal to R, then beta 1 is equal to beta. You will get the same value for both the areas. So you can replace beta 1 is equal to beta 2 is equal to beta. So this parameter if you substitute here, okay, delta PD1 plus here the A12 also will be 1. Okay, when you considering both areas are identical, this A12 also will become 1. Okay. When you substitute these all in this expression, delta PD1 plus A12 is 1, delta PD2 divided by A12 is 1, beta 1 is equal to beta 2 is equal to beta, therefore beta plus beta 2 beta. Okay. So that's what we are represented here, delta PD1 plus delta PD2 divided by 2 beta. At the same time, delta beta12 with the same assumptions. So these two, beta 1 is equal to beta 2 is equal to beta. If you take this common, beta into delta P2 minus delta P1 divided by 2 beta. Okay, beta and beta will get cancelled. So delta PD2 minus delta PD1 by 2. Okay, by taking these assumptions, you can write the expression for both the change in frequency and change in time and power. Okay, so these are the final expressions when considering both the areas as identical. So you need to consider two parameters, one is change in frequency and change in time and power. Okay, in the next, if you say when the load disturbance occurs only at area 2, okay, we are considering a specific case, we are saying that when the load disturbance occurs at area 2, for example, means load is changing at area 2 only, means the change in load in area 1 is 0. There is no change in load in area 1. Okay, we are considering the case that the load disturbance occurs only in area 2. So delta P2 is there. But the change in load in area 1 is 0. There is no change in load in area 1. Therefore, delta PD1 is equal to 0. We are taking just a specific case. When you substitute this here, delta PD1 is 0. So delta F is equal to delta PD2 by 2 beta. Okay. Next, delta PD1 is equal to delta PD2 by 2. Okay. So from this you can say that, from this you can conclude that when there is disturbance occurs in area 2, when the disturbance occurs in area 2 of magnitude delta PD2, okay, delta PD2 is a magnitude that is change occurs in area 2. So half of the amount will be half delta PD2 by 2. So half of the amount will be transferred from area 1 to area 2. Okay, so you need to understand here, when the disturbance occurs in only area 2, the disturbance occurs in area 1 is 0. That is delta PD1 is 0. So there is no change in load in case of area 1. We are considering the change in load in area 2 only. And this magnitude is delta PD2. Okay, we are considering the magnitude of change in load in area 2 is delta PD2. So from this expression you can conclude that, okay, the half of the amount of change in load in area 2, half of the change in load in area 2, that will be transferred from area 1 to area 2. Okay, so that we need to observe here. So these are the two parameters under steady state condition we have to study. Summary. Okay, so we have reduced the block diagram with certain assumptions. We have reduced block diagram with certain assumptions for obtaining steady state parameters of change in frequency and change in time and power. Okay. In case of area 1, the area control error will be consist of only a single parameter, which is change in frequency. In case of area 2, that will be contributed by the two parameters, which is change in frequency, at the same time the change in time and power also. Okay, in case of two areas, these two parameters will contribute to the area control error. So that's why if any disturbance occurs in a system, you need to study the change in frequency, at the same time the change in time and power also. Okay, so by considering, second point is by considering step load change. Step load change in the system. We have derived the expression for change in frequency as well as change in time and power. Okay. The same expressions are reduced by considering the two identical areas. We are considering single area 1 and single area 2 of identical in nature. So two identical areas, and we have derived the expression for same delta F and delta P type 1. So as we are seeing the specific case that we have seen a specific case also that when the load change occurs only in area 2, when the load change occurs in area 2 only, half of the amount will be transferred from area 1 to area 2. Okay, so these are the summarized point from the today's session. So in the next session we are going to study the dynamic analysis of a two-area low frequency control. Thank you.